I'm going to show you how to create a solution for the damped harmonic oscillator, and this is the viscous damped harmonic oscillator. Okay, so let me explain the situation. I'll review an undamped harmonic oscillator, and then we'll get to work. There's a lot of stuff that we have to do, and then we'll make a graph of it to show it numerically. We'll do all that stuff too. Okay, so in a normal harmonic oscillator, we have some mass connected to a spring, and if we pick x equals 0 as the equilibrium position, then the amount that the spring is stretched from the equilibrium position is x, and the restoring force would be negative kx, where k is a spring constant. So that's the normal spring. And I have a video on 3 solutions to this, but let me just say, in that case, I could say the net force is negative kx. I could write that as mass times acceleration, where x double dot is the second derivative with respect to time. That's just the way we like to write it for shorthand notation. And if I divide both sides by m, and I can solve for the solution, I don't have to divide by m, but if you do. And this is the generic solution, one of the generic solutions for the simple harmonic oscillator. It says x as a function of t is x0, this is the starting position at t equals 0, times cosine omega t, plus v0, the starting velocity at t equals 0, divided by omega sine omega t, where omega is the square root of k over m, the spring constant of the mass. Okay, so that's the undamped, and we want to use that to compare with our damped oscillator. And really the only thing that we have added here is we still have that restoring force, negative kx, but I also have this drag force. So x dot is the direction of the velocity, and we're in one dimension here, as you can see, times some parameter b, that's the drag coefficient. So imagine like not a mass on a surface, because that'd be a constant force. Instead, we're going to have like a mass in oil, and so that's like oil. And as it moves through the oil, then there's a force that depends on how fast it's moving. The faster you move, the greater that force. So with this equation right here, I want to solve, let's just write this as mx double dot equals negative kx minus b x dot. That's the equation we want to solve. Let's move all these terms to the other side. Actually divide by m. X double dot equals negative k over m minus b over m x dot. Oh, I missed the x. And now I move them all to one side. I get x double dot plus k over m x plus b over m x dot equals 0. And so this is kind of a strange equation, and I should write it like this. X double dot. Let's actually make some substitutions right away. And these are the kind of substitutions like, why the heck would you do that? And you don't see why you do that until you've already done it. So I apologize beforehand for that. But trust me, we could do this the complicated way or the better way. And the better way is to make these substitutions. It doesn't really matter, they're just constants. So I'm going to say omega naught squared is k over m. It's right there. And that makes sense over here, right? That's the undamped frequency would be omega naught squared would be k over m. And then this, I'm going to say beta is some parameter. I'm going to call that b over 2m. And now that one's like, I don't know why you would do that until you do it. Okay. So if I make those substitutions, I get this. X double dot plus omega, no, I'm going to put the b. Plus, this is going to be actually 2 beta x dot plus omega naught squared x equals 0. Now, I mean, that's a pretty tough differential equation to solve, so we're going to do it anyway. Let me write this out as a derivatives. The second derivative, which is this, of x, right, to take the derivative twice, plus 2 times beta times the derivative with respect to x plus omega naught squared times x equals 0. Now, this is kind of a trick, but I can write this, just imagine, close your eyes and imagine. And imagine that since I have this derivative of the derivative, what if I just write this as d equals the derivative with respect to time? It's an operator. In that case, I have the operator twice, so this is like d squared. So I have an x there. Let's just write that out. D squared x plus 2 beta dx plus omega naught squared x equals 0. Now with this, I can actually factor out the x, and I get d squared plus 2 beta d plus omega naught squared. All of that operated on x is equal to 0. So, I mean, the solution here is that x, I don't want x equal to 0. I want this operator to be 0, which makes a little sense because it's not actually going to be equal to 0. But if this term were 0, then this equation would work. And d is the derivative operator. Okay, so let's put this on another page. Let me write that out. So I have this. I have d squared plus 2 beta d plus omega naught squared x equals 0. This is sort of like, imagine that I could do this. Imagine since I have a d squared, a d, and a constant term, I should be able to do this. D, I'm going to write it as minus just because it's easier that way. Minus r1 times d minus r2 x equals 0. I should be able to factor this. I should be able to factor this into two factors, two terms. Now, they may not be easy to do, but I should be able to do that in theory. So if that's the case, then either this d minus r1 operated on x would be 0. So either this, either d minus r1 x equals 0, or d, that's a d, that's a parenthesis, minus r2 x equals 0. So now let's switch back to our notation. So this says if I operate d on x, I get x dot. That's still equal to 0. D on x is x dot minus r1 x equals 0. Or x dot minus r2 x equals 0. So there's two different constants there. And I can solve this equation, right? Because now if I add r1 x to both sides, this gives me x dot equals r1 x. So it says, what do I take the derivative of x? And I get r1 times x. And the answer is x equals c1 e to the r1t. Remember, those are time derivatives. And so I have a constant out there because it doesn't really matter. I need to include that there, though. The constant will still be there, and it'll still be there. But that would work, right? If I take the derivative of this, I get c1 r1 e to the t, which is r1 times the function x. And the same thing down here, x dot equals r2x. So that gives me x equals c2 e to the r2t. So if each of these are a solution, a linear combination of them must also be a solution. So that gives me the solution to this would be x as a function of t would be c1 e to the r1t plus c2 e to the r2t, where c1 and c2 are constants and r1 and r2 are from the factors of this equation. That's important right there. Now, I have 1 times d squared plus 2 beta d plus omega naught squared, and I don't know what those factors are by doing it manually, but I can do it using the quadratic equation. So this is like this: a d squared plus b d plus c equals 0. Then the factors are going to be equal to, so r1 and r2. r1 is going to be equal to negative b plus the square root of b squared minus 4ac over 2a. That's a quadratic equation. r2 is negative b minus the square root of b squared minus 4ac over 2a. Now all I need to do is put in my a, b, and c. So here I have a is 1. So let's write that right here. A is 1. B is 2 beta. C is omega naught squared. So that gives me r1 is going to be negative b, which is negative 2 beta, plus the square root of b squared, which is going to be 4 beta squared, minus 4 times A is 1, C is omega naught squared, all of that divided by 2A, which is just 2. And maybe now you can see why we had that 2 beta term in there. Because right here, I can factor out a 4 out of that and take the square root, and I get 2. So then I can factor out the 2 out of both of these two terms. I should write that out. So it's going to be negative 2 beta plus 2 square root of beta squared minus omega naught squared, all of that over 2. And what happens? Cancel, cancel, cancel. So R1 would be equal to beta plus the square root of beta squared minus omega naught squared, all of that. That's it. I canceled it too. Okay. And then R2 is the exact same thing, except this is a minus sign. So I can say R2 is beta minus the square root of beta squared minus omega naught squared. So now I can put those back into my function right here, and I have a solution. I don't know C1 and C2, but we'll find those in just a second. Okay, so that means I have x as a function of t. It's going to be C1 e to the okay, I have that. I'll write it out. E to the beta plus the square root of beta squared minus omega naught squared t. And you can't see that. That's how bad that was. You can't even see it. That's my fault. I apologize. Fix my paper here. Okay, plus C2 e to the beta minus the square root of beta squared minus omega naught squared t. So we can use a nice little trick here in that I have an exponential of a sum. This is equal to the product of the exponential. So I could write this as C1 e to the oh, that's all times t. That's times t. Beta t times e to the square root of beta squared minus omega naught squared t plus C2 e to the beta t. It's got that same term in there. E to the negative square root of beta squared minus omega naught squared t. And then I can factor out the e to the beta. So I get e to the beta t. I feel like this should be minus. Yeah. Wait. No. Yeah. Why is it minus? Oh, wait. Because that's minus. That's why. This is minus. That's the minus. I left that minus sign off there. That was my fault. Okay. You see, when you've done it before and you get to this point like that, and you're like, wait, what? So that's minus. That's minus. That's minus. I knew that's because it's exponential decay. And then I have C1 e to the square root of beta squared minus omega naught squared t plus C2 e to the negative square root of beta squared minus omega naught squared t. Okay, so now I need to find C1 and C2. So let's say that, let's do a simple case. Let's say I pull the mass to some position x0 and let it go from rest. So at t equals 0, x of 0 equals x0. X dot of 0 equals 0. Okay, so if I just put in t equals 0 up here, let's see what I get. So x of 0 is going to be e to the 0, which is 1. So that whole thing's 1. And then I get C1 times this is 0. So I get 1 plus C2. Is that right? Yeah, because this is going to be t is equal to 0, so that whole thing goes to 1. Yeah, so C1 plus C2 is equal to 0. I mean x0. So I don't know C1, I don't know C2. That's fine. Okay, now I can take the derivative for x dot. So let's take the derivative of this function. So that's a little bit more complicated. X dot as a function of t, I'm going to need to take the derivative of this, which is going to be negative beta e to the negative t times all of that stuff. I'll just put it, can I just put it in parentheses? Yeah, it's all that stuff. And then I need to take the derivative of this times that. So it's going to be plus e, that's a beta, e to the negative beta t. You know what? I want to do this, but it's just going to get messy. Let's just pick c1 equals x0 over 2 plus c and c2 equals x0 over 2. Let's see if that works. Okay. Okay. So let's go ahead and see if this solution is legitimate. But in fact, there are a couple things that can happen depending on this, right? First of all, we can do the following. What if there is no damping? No damping at all. So beta is equal to 0. So right here, if beta is equal to 0, that term's 1. Here I get 0 minus omega naught squared. So that's going to be an imaginary number, and that's going to be an imaginary number. And so one of the ways that we wrote the solution to the undamped motion was this. I'm going to put it in a box because it's undamped. X as a function of t is c1 e to the I omega t plus c2 e to the negative I omega t. And it turns out that that is a solution, and it does equate to sines and cosines. And that's exactly what you'd get if beta is equal to 0. So that's a good sign, right? That says, hey, we're not in the wrong direction. Okay, but what I want to do now, and I'm pretty sure I can pick these, I want to make a plot. I want to make a plot of this function with some parameters. Let's go ahead and pick some values. So let's say m equals 0.05, beta, all right, it's called as b. B equals, I'm picking a number here. If it doesn't work, it doesn't work. 0.1, K equals 5. X0 equals 0.1. Okay, so let's take that, and I want to make a model two ways. First way I want to do it is make a numerical model. So this is actually pretty easy. Suppose I have my mass like there. There's going to be two forces acting on it. I have the spring force, negative kx, and then I have the drag force, whichever way it may be. Let's say it's this way, negative bx dot. So I can calculate those two forces. So then I can say F net x equals negative kx minus bx dot. That's it. If I assume that I break this into a small time step, let's say delta t equals 0.001 seconds, then I can assume that force is constant over that time. So this would mean that the acceleration, I'll write it as a, is going to be negative kx minus bx dot over m. I have to divide by the mass. And that would be equal to the change in velocity with respect to time. And I'm assuming that's constant, so I can write this as a finite function, a delta. And if I consider v2 the velocity at the end of the time interval and v1 at the beginning of the time interval, after I calculate a, I can solve for v2 at the end of the time interval. v2 equals v1 plus a delta t. Now I can do the same thing with velocity. I can say the velocity is equal to the change in x with respect to time. And if I assume this is constant during the time interval, which it's not, then I get x2 equals x1 plus v2 delta t. So in that case, I'm using the velocity I just calculated up here, so I'm putting v2. And then I can update time. t2 equals t1 plus delta t. And then up here, I'm going to write up again, a equals negative kx minus bx dot over m. So I'm going to do 1, calculate the acceleration. 2, use that to update the velocity. 3, use that to update the position. 4, update time. Come back up here and do it all again. So that's my numerical model. And I can do it that way and then do it with the theoretical solution and see if they're the same thing. So let's do that. And of course, since we're going to break this into time steps, if I want to do 1 second worth of data, it would take 1,000 calculations, 1,000 loops, and I don't want to do that. So I'm going to do it in Python. So let's jump over here to Python and let's make this happen. Okay, Python. So I'm using GlowScript v Python like I always do. I'm not going to make a model of it. I'm just going to plot it. So let's first make a graph. G1 equals graph. X title equals time. I'm going to plot X versus time. Oops, that's not supposed to go there. Is that big enough? Y title equals X in meters. And then I need to do this. Width equals 400. Height equals 200. Otherwise, the graph just ends up being too big in terms of the way I capture this, and it looks too bad. And I'm going to make 2 graphs. I'm going to make Fn for the numerical plot. Fn equals G curve. Color equals color dot blue. And then I'm going to make Ft for the theoretical. G curve. Color equals color dot red. And then hopefully those 2 things will be on top of each other. But we're going to first start off with just a numerical. So T equals 0. Dt equals 0.001. I'm just entering my other parameters that I had. M equals 0. What did I say? I said 0.05. I said B was 0.1. K was 5. And X0 is 0.1. Okay. So now let's say while t is less than 3. I'm just going to run it for 3 seconds and let's just see what happens. I'm not gonna do an animation or anything like that. So the first thing I need to do, like I said, is to calculate that acceleration. So I'm just going to type out my equation. A equals, looking at my equation, parentheses, negative k times x, which I didn't have. I'm going to put that in there, minus b times x dot, which is v. So I actually need to put these variables up here. I can say x equals x0. That's where it starts. And v equals 0. That's its initial velocity. And you may think, why are you doing x0 equals x and then saying x? Because I'm thinking about the future. And then I need to divide this by m. So that's my acceleration. Now I'm going to use that to update the velocity. So v equals v. It's still not big enough. V equals v plus a times delta t. Just like I said. Now, if you haven't seen this before, that's a position update. That's a make equal to equation sign, not an algebraic equal sign. Now I'm going to do the same thing for x. X equals x plus v times dt. Update time. T equals t plus dt. And now I'm going to make the graph. So fn dot plot tx. And let's see if that works. I didn't even save it. That's how risky I am. Oh, that's right. It worked. I was thinking, why is it damped? I didn't tell it to be damped. I did tell it to be damped, right? I did tell it to be damped. I have a damped term over here. Let's see. Let's save this. I'm going to give you the code. Don't worry about writing it down. Damped oscillator. Save. Okay, let's just check. That looks good, but let's check. What if I multiply b times 0? I know then I have no damping in it. It should be simple harmonic motion. So I think I'm happy. I hope you're happy. Right? Okay. So I'm happy. That's what matters. So I think we have the numerical model working. Okay, so now we just need to calculate my other terms. So let's say this. C1 equals x0 over 2, and I'm not 100% sure about this. C2 equals x0 over 2. I need beta, right? Let's just call that capital B, and that's going to be equal to, what did I say beta was? Was it, it's b over 2m. B divided by 2 times m. And do you see now why we use 2m? Because that allows us to factor out that 2 out of the equation. It's not wrong to not put 2. It just makes the equation a lot simpler. And then I need omega naught. Omega 0 it's going to be the square root of k over m. So now I have all my parameters. I can calculate the theoretical x. I'm going to call it xt is going to be equal to it's exponential, I think, negative beta times t times c1 times exponential of, what would it say? It's square root, right? Square root beta squared minus omega naught squared. That's the square root, that's the exponential, plus c2 times exponential square root negative square root beta squared minus omega 0 squared. Kind of nervous there. Okay. And now let's plot that. Ft dot plot xt xt. Not high confidence here. That's fine. Let's just do it. See, something happened. It didn't plot it at all. Huh. Let's see. What the heck happened? xt. Let's just print down here. Print xt. Not a number. Okay. Okay, let's check something here. Glow script. Help. Work with 3D objects. Math. Functions. Okay, what do we have? exp to the x. So it is e to the x. So why is that not a number? So I must have typed something wrong in my equation down here. Okay, let's just try this. Print, let's say, let's print this. Let's run the whole thing, and then print, oh, that's weird. Print, doing it again. Print, exponential negative b times t. So t is not 0, so it should print a number. Let's just see if that does it. It'll run the whole thing, and then we can see if it prints a number. Okay, it did, so that's good. Now let's try this. I'm going to print just that. Ooh. Okay. I think that's right. Right there. From here to there. C1 times. I did say C1. I did define this. Okay. So let's print this. That should be something. Maybe it's an imaginary number. Okay, that's the problem. Let's do this. Print B, print omega 0. So B is 1 omega 0. See, so what I did was I actually overdamped it. No, I underdamped it such that that solution doesn't work because I actually get imaginary numbers when I take the square root, and we can fix that. Okay, we can fix that. But let's instead change this, make it more highly damped. So what if I have B is 11? Okay, so it worked that time. And in fact, it worked really too well. Let's actually run this for a much shorter time. Let's say 0.1 seconds. There. Oh, but now the two, that looks good, but that doesn't look good. Okay, I think I need to go back to the paper and do I want to go back to this one because that one actually looked good. It just didn't work for that solution. Okay, so let's do that. Oh, there we go. No, I did it for too long, too short. So let's change this to 3 and run that. Okay, so let's go back to the paper and fix this. We can fix it. I know we can. Okay, going to paper. So here is my solution. I have this. X of t equals e to the negative beta t times c1 e to the square root of beta squared minus omega naught squared times t plus c2 e to the negative square root of beta squared minus omega naught squared t. Now, the problem is that if beta is less than omega, then that's going to give me an imaginary number. And Python's like, I don't know what you want me to do. It's an imaginary number. I don't know how to handle that. You've put me in an uncomfortable situation, and I feel uncomfortable. That's what Python actually says. So let's call this the square root of beta squared minus omega naught squared. And let's assume that that term inside is negative. So I'm going to write this as equal to I times the square root of omega naught squared minus beta squared. Right? Because if I switch the order, I include a minus sign, and I can factor out that minus sign and get an I. And then I'm going to say omega naught squared minus beta squared is equal to some other frequency, omega 1, just to make it easier. So this becomes omega 1 squared. So that becomes, this whole term becomes I omega 1. And now I can rewrite my whole thing. X as a function of t equals e to the negative beta t times c1 e to the I omega 1 t plus c2 e to the minus I omega 1 t. Now, in my video on the solutions to the simple harmonic oscillator, we got this. And I showed that this was the same as this. It's the same. All three solutions are the same. But I can rewrite this part in here as equal to e to the negative beta t times. Now I can do this as a cosine omega t plus b sine omega t, which is what I'm going to do since I wrote that before. And actually, so where did I put that? So I'm going to say a, which is actually I wrote it as x naught cosine omega t plus v0 over omega sine omega t. It's the same thing. And if you don't believe me, go back and watch that video. I'll link that video down below. So this is just a normal oscillating term, and this is an exponentially decaying term. So the classic way of drawing this, which now I can calculate all this stuff, is like this. So I have an oscillation, and then I have a decay, a decaying amplitude. And so if I put those two things together, I get, here's my decaying amplitude, and that's what I had. So, but we can plot it this way, right? I can change that solution. All I need to do, I have my B term, or my beta term already. I have V0 with 0, so it's really just cosine. Okay, so now let's go fix that back in Python because I have to have it fixed. It's required. I'll get fined if I don't, and I don't want to fine. I can't handle that. So down here, I'm just going to change this. I'm going to keep that term. I'm going to change all this exponential term, which is imaginary, so I'm going to replace it with that oscillation of x0, and C, good thing we put that in there, times cosine omega, in this case, it's omega 0. No, it's omega 1 times t. And so now up here, I need to say omega 1 is going to be equal to the square root of omega 0 squared minus, ooh, that's an O, omega 0 squared minus beta squared. Okay, I think that should work. I don't need to print that stuff, but I'm too lazy to get rid of it. Yes. Okay, I don't know if you can tell, but if you look in really close, that is the same thing. The red, I printed the blue and then the red, and they're right on top of each other. They're right on top of each other. If you don't believe me, let me add this. Let's say, let's shift it up by 0.01. So I'm just going to add 0.01 to my solution just so it shifts up and you can tell that they're different. There. So, but other than that, they're the same. And this is really important because I use forces and numerical calculations to do that. And I also did that with solving a differential equation, in this case, a complicated one, but we did. And there you go. Okay, so the things to remember: number one, this code down below. Number two, my video on the undamped harmonic oscillator down below. I guess we should check, right? What if if B is equal to 0, this whole thing should switch back to the way it was. Let's just double check, multiply this by 0. That way I don't have to actually change it. There. It's slightly different, and that's, oh, I did shift it up, that's why. I forgot. I added that one thing. Okay, so there you go. I'm done here. I'll talk to you guys later.